Architecture Part 1. As storage providers, we have obligations to storage clients. Client makes a storage deal with us and sends us their data. We're expected then to store the data that they send us and maintain it over time. We need to store it somewhere safe, ensure there are no flip bits. That's what we're expected to do. But on a decentralized network, we are not and should not be trusted to just do that. Instead, we have to prove to the network that we're actually meeting our obligations. So the Filecoin spec, the specifications, is a comprehensive document that defines how a storage provider interacts with the Filecoin network and how specifically we prove to the network that we're meeting our obligations. It's hosted at spec.filecoin.io, and it's quite wordy, but it's the important base for how we architect our actual storage providers. At the most fundamental level, the entire architecture of a Filecoin storage provider is bounded by the spec. The storage provider systems that we architect and build have to meet those requirements, and if we do fail to meet the requirements, then there are penalties defined in the spec that we are subject to. A well-architected and well-run storage provider won't incur these penalties, but their presence serves a valuable function to the network in that it decentralizes the trust. Because a storage client knows that any rational storage provider is going to avoid incurring these penalties. And as storage providers, we avoid incurring the penalties by constantly proving to the network that we are meeting our obligations to store the client's data and to protect its integrity over time. As such, the client can be assured that the storage provider has a strong incentive to store and maintain their data for the agreed upon duration, even if they don't otherwise have any knowledge about the storage provider or trust the storage provider. When we initially receive the client data, we first have to put it through a one-time computationally intensive process called sealing. Sealing data encodes it into a form ready for the proving process. The first proof our system needs to generate for the data is called proof of replication. Proof of replication is a procedure by which a storage miner can prove to the Filecoin network that they have created a unique copy of some piece of data on the network's behalf. So that's the data the client sent to us. We prove we've received it in one piece, and proof of replication therefore is used in the Filecoin system to generate the sealed data. It's the mechanism by which it happens. The practical implication of this part of the spec is that the capacity of our storage provider system to perform the proof of replication determines the maximum rate that we are able to ingest client data and the speed at which we can start proving to the network that we have stored the client's data. The next proof that we will need to be able to generate is called proof of space-time. Proof of space-time is Filecoin's audit check on the integrity of the client's data over time. The proof of replication is the initial proof that we've received the data, and then proof of space-time will check that we are maintaining a copy in good order for the full duration of the deal. So we need to perform the window proof of space-time. It's called window post for short, on a random subset of the data. It happens every 24 hours. And the more data that the storage provider stores, the more window post computation that they need to perform in one day. And that translates to more hardware being required if there is more storage to prove. And the different data needs to be proven at the different times in the day. So the hardware has to effectively have continuous ability to do this. There's no shortcuts to doing it. The other proof of space-time that we perform is called winning proof of space-time, or winning post. And it's another audit check on the integrity of the client's data. That's performed at random intervals, whereas window post happens same time every day. Winning post can happen randomly. We need to have the data at that time to succeed with winning post. The more data that the storage provider stores, the more frequently they are subject to this winning post audit check, the more frequently they have to submit proof that they have successfully still stored a copy of the client's data. If the storage provider that we build fails to meet those obligations, then the network imposes penalties upon us, and it's called slashing in the spec. And broadly, we can split the different types of slashing into consensus faults and storage faults. The bulk of the responsibility for ensuring that our storage provider is not slashed by the network falls on the shoulders of the software that we use to interact with the Filecoin network. So even though it sounds quite severe that we may be subject to penalties, most of the time we don't have to worry about it because it's actually just taken care of for us. It's just making sure that we're doing what we've agreed to do. The network protects itself from anyone writing their own software, essentially, that tries to interact with the network in malicious ways, which won't happen if we're just using normal supported software. And as rational and well-behaved network participants, we only need to be concerned with ensuring we use reliable hardware that's able to perform the calculations correctly, just let the software do its thing without causing errors that incur any of these penalties. So the hardware we do use and that we do architect has to perform these proof computations consistently without error, and it needs to store the client's data safely on a storage system that maintains its integrity, because random parts will be chosen for auditing. We don't know which parts, it just needs to all be in one piece. And of course, if the client wants to download their data, I'm sure they will want it to be in one piece, stored correctly. But as we can see, the participation in the Filecoin network pushes us towards providing a reliable service, because it's not just on the honor system. We will lose out if we fail to do so. For each client deal, every 24 hours, we have to submit a window post proof to the network. The proof has to be computed within 40 minutes and submitted to the network within a 30-minute window. If we fail to do so for 2 consecutive days, then we will begin to incur fines. So this isn't a problem as long as our systems are built to compute window post reliably and send it to the network reliably. Then this essentially isn't a concern. Randomly, we'll receive the winning post challenges as well, as mentioned earlier. And for those, there's 30 seconds to generate the proof. So it pretty much rules out storing on tape medium, for instance. It's too slow. Have to use some kind of online storage system, hard drives, for instance. It's only 30 seconds. But if we don't submit that proof, then nothing actually happens. So in that sense, we don't really need to be that concerned then about computing winning post, because nothing bad will actually happen if we don't do it. But the difference here, though, is when we do submit winning post to the network within that 30-second window, then we will receive a fill reward. It's called the block reward. And so if nothing happens, then we haven't received that reward. We're incentivized to perform the winning post to get the reward. If winning post is the carrot really dangled in front of us to make sure we're performing our obligations, there's also window post is the stick that punishes us if we do not. We've got to keep both in mind. Again, both are just taken care of by the software that we use. Generally, if it's architected correctly, we don't have to worry about it, but this will stop anyone just playing fast and loose and losing people's data or anything like that. So I strongly recommend that the storage provider can compute winning post on time to be able to get those rewards when they're available. So with the Filecoin specification in mind, let's move on to the practical implementation of the spec using Lotus, which I'm sure has been talked about. It's currently the most feature-complete implementation of the Filecoin protocol, and in practice, it's what is the main one that is used to store client data at the moment. It's seeing the most development. It's the most advanced software right now. So these are the components of Lotus. It's modular. split into separate parts. All of these components could be run on a single machine, if desired, or they can be run on multiple different machines, anything from one machine to multiple racks of servers. It's all possible depending on the aim of the storage provider, how much throughput we're looking for, what capacity we want, how efficient we want it to be. And this is why we can really innovate compared to other storage providers, because maybe we have a better idea about how to build our servers that's more efficient. If so, we just need to run the parts of Lotus on appropriate servers, and we can realize that efficiency. It's important to size the different parts of the hardware appropriately, depending on what we're going for. If we want to be able to store deals more quickly, or if we want to be able to just store more storage, it will determine really where the priorities are with how we size the equipment for these different components. So the flow of the client's data should be considered, and it's important to size the fabric of the network appropriately so that we can push all the data around between the processes. If they're on different machines, the network needs to support that, and the equipment needs to support that. Perhaps we're receiving data from clients on hard drives through the mail, then maybe we wouldn't need such a big internet connection. We could just optimize that way, and we just need the ability to read those drives quickly. Whatever the priorities are, then that's what needs to be considered. So let's have a look at the individual components in some more detail. Firstly, the Lotus node provides the functionality that we need to participate on the blockchain. It synchronizes its state with all of the other Filecoin nodes on the network, and it allows our storage provider to make deals with storage clients. This is also where one of Filecoin's major strengths is implemented and comes into play. It's got a scalable and functional proof-of-stake system, which enforces security of network. So I'm sure everyone's heard of blockchains consuming a lot of energy, quite a lot of energy, as much energy as small countries. But those rely on proof of work, which is just a brute force method to secure a blockchain, where you're just using hardware as fast as possible, using as much energy as possible just to compute a big long string of zeros and compete on who gets the longest string. That's how proof of work works. But this isn't necessary in Filecoin because it can use its storage proving process to secure the network in an energy efficient way. Really just the cost of just keeping hard drives on. There's no need to do any of that kind of intensive mining at all. So big strength of the Filecoin network. And the Lotus node, would usually run on its own machine to make sure it can stay in sync and it's got consistent performance. So usually it's necessary to run one copy for high availability. Sure, two makes sense. But generally one. And then the Lotus miner process is what will coordinate the storage provider's sealing and proving activities. And it's where the winning post and window post proofs are actually calculated. So it's important there that we have, reliable hardware to make sure those calculations are correct. So maybe graphics cards with ECC memory, error correcting memory, servers with error correcting memory, and enterprise grade hardware. It's all a good idea just to make sure there's no errors in the software that would result in possible penalties or problems down the line and problems for the clients. The miner also contains the Lotus markets component, and that can be run inside the miner process, or it can be split out to run separately. The markets process is responsible for essentially advertising the storage providers to the rest of the network. It allows clients to find the storage provider and then send their data in online. It can show storage price and allow automatic deal making. We set the price we're willing to accept, and we can make an allow list of clients we're going to accept. And the markets process is what's actually on the internet, and receiving and sending that data. When clients want their data back, then they can make retrieval deals happening through the markets process. Again, that will coordinate that deal and send the data to them. And because it's connected to the internet for security and to reduce the risk to the proving functions performed by the main miner, because of possible software hardware issues, and to provide increased performance for markets, it's a good idea to run it on separate hardware. Generally good practice. Just keeps things separate, means we can just have those separate processes running the best they can and not interfering with each other. So depending on requirements, depending on how important that is, maybe we're not actually looking to accept that many deals. Maybe one machine makes sense and we're just saving money, or maybe we want to accept a lot of deals. We split it out to multiple powerful servers. So 1 or 2 machines generally for miner and markets. And then the Lotus worker processes are the ones that can use a lot of hardware if we want, or just one machine, but it could be one machine, could be many racks worth of machines. Usually we'll run at least one worker on each individual machine that we use for the sealing process. The workers connect back to the miner, and just essentially when the miner receives data, it needs to perform sealing on the data. It will send it over to the worker to do the actual sealing. So the amount of worker machines we have, amount of worker processes we have running, that determines how much data throughput we can have, how many client deals we can seal at the same time. So it's very important to scale that appropriately. If we scale it too high, it could be wasteful. But it all depends on the aims. And it's really where we need to optimize if we really want to seal data quickly. So again, could be 1 machine, 2 machines, or it could be multiple racks in a data center if we want to seal petabytes per day. Then we'll be looking at a lot of machines. The sealing processes that we complete when we receive data, I'm saying we complete. We don't really have to do anything once we've set the data up. The software just does it, but it's what we have to size the hardware for. It's split up into a few different steps that have different requirements, and it's possible to run these on an all-in-one machine, but then if we split these steps out into their own machines, it can be more optimal. The process starts with a task called add piece, where it's taking client data and putting it in a block of 32 gigabytes or 64 gigabytes, and it's called a sector. Stored on blockchain as a sector, and the blockchain recognizes sectors. Each sector can contain a deal from one client, maybe a deal from another client, put all in one sector, and it will get sealed together in one 32 gig, 64 gig chunk to then be proven and put onto the network. The add piece part takes a few minutes, so I haven't put it on the slide, but it's if we're really splitting out everything, we can put the add piece process onto its own separate hardware. But the majority of the work is really split into 3 different parts. There's pre-commit 1, pre-commit 2, and compute 2. And they're shortened to PC1, PC2, C2, respectively. And that's what we see when we're running commands in Lotus. It'll just refer to PC1, PC2, C2 as the pre-commit 1, pre-commit 2, commit 2 parts of the sealing process. And generally, pre-commit 1 will use 4 CPU cores for around 3 hours per 32 gigabytes of data that we're sealing. Consumes around 65 gigs of RAM and uses around 460 gigs of high throughput storage. This could be anything, but in practice, usually NVMe storage is used to provide the required throughput. If it's slower, then it's just going to slow the sealing process down. So we generally need to look for storage devices that are capable of high endurance. So they usually advertise having a high drive writes per day rating, DWPD. And It's mainly due to the amount of data being written during PC1, because every 32 gigs of data we store, it is using 460 gigs or so or more to do the computations. It's only temporary, but it'll have written that data and cause some wear onto the disk. So we just can't use off-the-shelf consumer components. They'll just wear out. But if we use enterprise class hardware, then it's no problem. It'll last 5 years plus. It's just something to keep in mind if you use suspiciously cheap storage drives that are really meant for storing some games on or something. Then you can run into problems. But if you're using some hardware that basically has these specs, then it's perfectly capable of holding up. Some drives also can't maintain that throughput under load. Again, really it's the consumer drives that can't do that. We're just looking for enterprise hardware that's got these abilities to just perform consistently and reliably for a long period of time, so it just protects the investment. But generally, enterprise class NVMe drives are going to work fine. After PC1, it's about 3 hours on that, then PiKNiK 2 follows straight on afterwards after PC1, uses a lot less RAM. Not sure specifically how much, but a lot less. It's much less to worry about. But it does use the same storage space temporarily, same kind of NVMe required there, and it uses a graphics card as well to speed up the proofs on that card. Usually quite a powerful graphics card. We're looking at cards designed for workstations or data center use. Generally, it's discouraged to use gaming cards in data center settings, various reasons. Okay, there's a point after PiKNiK 2 called wait seed, and it's not on here essentially because it's enforced by the network. It's not a point where any computation happens. It's just waiting for security reasons on the network. No computation happens. It's just over an hour. Where we just have to wait before we can start the commit to part. Then commit to starts C2. The commit to part of sealing doesn't use its own scratch space like PiKNiK 1 and PiKNiK 2. It doesn't need the NVMe storage, but it does use a powerful graphics card. So similar to PC2, it just uses this card to efficiently perform the computations required to generate the proofs that get submitted to the blockchain. It also uses quite a reasonable amount of system memory for commit to, so it's pretty intensive on GPU and RAM, and we have to keep this in mind when we're choosing the size of our system. We could run all these processes on one machine and that would work fine, but if we really want an efficient sealing process, we split the processes out, put them on appropriate hardware, and we can get consistent times, efficient use of hardware. And really it is these separate processes that are the ones that we need to target. So here's some examples of what you can expect for your money. Starting at around $5,000, we can get an all-in-one machine. It can you can run the Filecoin node, Filecoin miner, the Lotus node and miner, perform the sealing processes all in one machine. We can easily get 256 gigabytes per day sealing capacity in that. We're looking at least 128 gigs of RAM in that, and some NVMe drives. It's more suitable for testing purposes, or a really small scale storage provider. It's very limited in throughput and expandability, but you could add machines to it later. But it's the smallest system that a storage provider would realistically look at running on the network. If we move up to around $30,000, then we're able to split out the Lotus miner and the Lotus markets processes into their own dedicated machines and have a dedicated worker machine that's responsible for completing the sealing tasks. This can be efficient as each machine then can be sized specifically for the priorities of the storage provider, and dedicating hardware to each component provides more predictable and consistent performance for each of those components. If we looking to spend around $100,000, then we can further increase the sealing performance and the efficiency through the use of dedicated machines for all of the different sealing processes. And Benjamin has a video on this topic, and he will be presenting part 2 of this architecture presentation in module 3B. So he may have something to say about that as well. If we're going beyond that, then we're looking at creating enterprise scale systems, really, where we've got, more enterprise style, high availability and reliability. We're looking at more like around 750,000 and above for an enterprise grade system. And for that, we can have high availability of the Lotus nodes, multiple miner processes to run separate storage providers spread out like that way, and increase the sealing capacity, the total throughput for serving deals and sealing them and proving them to the network from around about 30 tips per day to 1 petabyte per day or more, depending on what we'd like. And the amount of long-term storage should be factored into any of these, because a large sealing capacity may not make sense if the available storage would then quickly become full. We just have a load of sealing hardware that is sitting underutilized most of the time. But then if we have multiple petabytes worth of hard drives sitting around, but no way to seal to them quickly, then those drives are going to be underutilized. So we should match up the amount of storage we have with the hardware that we have available to seal onto them. Backups. So all the usual considerations apply when making backups of Linux servers. Lotus is almost always going to be run on Linux server these days, and you'd back it up in the normal ways. Specifically to Lotus, it's important to back up the Lotus miner. Specifically the metadata in the Lotus miner. It contains information about the tasks it's running on, the sectors that it's stored, and generally we want to just restore that state. A lot of it's on the blockchain, but for practical purposes, we don't just want to risk losing it. We want to be able to get it back straight away. So the Lotus miner has a command built in to perform a backup. Pretty easy to use. Just need to run it. It'll create a file that we then store on a separate server somewhere else. If we need it, we can reinstall Lotus miner. We can bring that backup back, but that is only the metadata in the miner. It's not the actual storage medium. That's a separate issue. The Lotus node itself, which is what keeps us in sync with the blockchain, if we do lose that, we can just create a new Lotus node and it can resynchronize with the blockchain. So that's not too great a problem. It's mainly time really taken to do that. We want to make sure we can do this in enough time that we meet client obligations, we don't get subject to any penalties. And the only consideration really in the Lotus node, we usually have the private keys for the wallets that are in use. So at least the control wallets in use for the miners, those specifically do have to be backed up somewhere, because if we lose those, if we only have one copy and we don't have those anymore, then we've just lost those wallets and we've lost all the fill in the wallets. We need to have those backed up separately. There's no possible way to retrieve the fill that those wallets contain if we do lose those files. But if the private keys for the wallets are stored in an insecure way, then they could fall into the wrong hands. That could lead to the fill they contain being stolen. We can't just back this data up anywhere. We have to consider backing it up somewhere securely. We want to make sure there's a copy somewhere, but we don't want anyone else to get a hold of those wallets. So those private keys should be stored in some kind of secure way, usually on an encrypted storage media, encrypted hard drive or something, and kept in a secure location, depending on what's important. Maybe put it in a safety deposit box in a bank, or just store it somewhere you feel is safe. Backups should also be tested as well, because they need to work when you need them. So it's good practice just to check that they're being made correctly now and again. Just make sure, maybe run a restore command. Just make sure it does actually restore what you expect. And nothing's been lost. The actual storage requirements for backing the metadata up of the Lotus miner and the keys for the wallet, it's not great. I mean, really, you could just do this onto one large flash drive or one separate machine. I mean, it's not a great requirement. It's mainly just security considerations and the ability to restore that backup that has to be taken into account. Well, the decision to back up the sealed sectors containing the client deals has large financial implications, because a one-to-one backup of that data is going to double the amount of storage that we actually need. We would need one amount of hard drives for the online data and then an entire new set for the backups. So due to this, some storage providers choose to not just create a one-to-one backup. Instead they use a fault-tolerant distributed storage system. Maybe, well, I mean, there's various available, maybe an object store or some kind of storage system that is able to provide the assurances they need that it won't lose data. It's got less overhead than the simple one-to-one copy of all the data, but there's that potential risk. I mean, it's one administrative domain. Someone could run the wrong command, delete everything. In practice, though, it's often done. Should be considered how feasible it is to move large amounts of data off-site if we are doing backups off-site. We could use network connections, high bandwidth network connections, or we might physically move drives. And the strategy employed by a storage provider does depend heavily on their individual circumstances and risk tolerance. It depends on the data you're storing and what the clients expect. Then business continuity. The considerations for business continuity, again, depend on the circumstances and priorities of a storage provider. The potential scenarios that are going to interrupt the critical business functions should be identified, and plans should be drawn up to recover those affected business functions and processes in the event of that scenario occurring. The Filecoin spec should be kept in mind during this process, because in general the ability to provide proofs to the network should be recovered within around 2 days to avoid significant penalty. It tends to kick in after about 2 days, so I want to make sure we can get back online within that time. And then considerations for high availability as well, and limited options really with Lotus software currently. It's under continuous improvement. Protocol labs are working on this, various tickets open, but currently what we're looking at is running multiple Lotus nodes to maintain synchronization with the Filecoin network, and we can place a load balancer in front of those nodes. Maybe standard software like Proxy or a hardware load balancer, and that can fail over between them. If one fails, the other one can be ready to take over, and that will keep a continuous node service available, keep us synchronized to the chain. It's not quite high availability, but then with the miner process, we can restart it quickly from the metadata backup if we need to on a separate machine. So have to restore it and restart it. The markets process can also be restored in the same way from a metadata backup. There's a backup and restore command in Lotus to do this. But the markets facility in Lotus is scheduled to be revamped to provide significant scalability and availability improvements. It should gain a more highly available feature set at that point. We're expecting that in not too distant future. It should, there's going to be a lot of improvements coming. The Lotus workers themselves are resilient, and if one worker fails, another worker can restart the task that the failed one was working on. So this is generally not too difficult to make sure we don't lose anything that way. And the servers we use, mostly for sealing. One option we can use is running each component of Lotus on its own dedicated machine. This will allow maximum specialization of hardware, but it can also be expensive at small scale and wasteful of resources if we're not always using those machines. If we haven't perfectly aligned the sealing process and we're not making balanced use of the machines. It's common then that we combine PC2 and C2, pre-commit 2, commit 2 stages of the sealing onto one machine, mainly because they both use a graphics card, so they can share that card. They can often run concurrently. We can run a PC2 while C2 is running. We might look at virtual machines, maybe a useful tool to split resources of the larger machine into separate units that provide consistency to performance of the sealing processes, and in the same vein, maybe containerized processes. That will do similar. For technical reasons, Lotus is more able to use resources efficiently when using virtual machines at the moment. So I'd recommend to use virtual machines if there's a desire to virtualize the components, but there's some, again, outstanding issues open on Lotus's GitHub repository, where PL are looking at fixing this, improving upon this area as well. So should be able to get more efficient containers as well in the not too distant future. Then the networking considerations. The market node needs to be reachable from the internet and should be on a server that has a publicly routable IP address or sitting behind a router that's capable of forwarding a port to it. The IP addresses of the market node are stored on the blockchain, so it's best if it does not change often, but if it does change, it can be updated on the blockchain if necessary. Each machine that the storage provider uses should have an IP address assigned to it, but the market node is the only machine that needs to be accessible from the internet directly. The Filecoin node, which is what synchronizes with the blockchain, can function with just outbound connectivity, but it's more optimal if it does have a port accessible from the internet. Again, it's up to the individual storage provider. Maybe security considerations kick in there, but it's more performance if it is accessible. Then the bandwidth requirements of the network depends on the sealing processes employed. We have to take this into account because we're spreading those sealing processes over multiple machines. We have to send a lot of data between those machines, maybe multiple hundreds of gigabytes of cache between PC1 and PC2 particularly. That's quite bandwidth intensive, so maybe we need 40 gig, 100 gig links. Security. When we create a new regular wallet in Lotus, the keys for the wallet are stored on the Filecoin node. So that server should be physically secured against unauthorized access, and consider if it makes sense to also use encrypted disks to further improve the physical security of that machine. Again, if someone accesses the keys for the wallet, then they could take the fill in the wallet. So it's really important to secure that machine. The set of people authorized to access the machines in the storage provider, both physically and over the network, should be limited to the smallest set required. It should be considered what appropriate legal precautions we can take, maybe contracts, NDAs, to protect the particular design of the network of the storage provider itself, and maybe other precautions like background checks on staff, anyone with access. The communication between the components in Lotus is extremely sensitive and vulnerable because it's currently unencrypted. So the components of the storage provider should only be connected together on a private network, definitely not over the internet currently, unless employing some kind of VPN technology to encrypt that traffic. By default, it's just unencrypted. We don't want anyone seeing that. If someone does gain unauthorized access to the miner process, then they can issue malicious commands, as you'd expect. So use standard techniques that will secure that server on the network, firewalls, for instance, as well as limiting access. And consider the results of human error. When we're sending money between the Filecoin wallets, it's easy to make a typo, and maybe we want processes in place where there's a check or some kind of process where that can't happen, where that's made, there are checks. We don't just type in the wrong number and suddenly send things the wrong way, because if we send Filecoin to the wrong wallet, then we can't get it back. We have to make sure this is correct. It's unrecoverable. If we stop the miner while it's performing the proof computations like window post, winning post, well, there's time limits on when those can be submitted to chain, so it could result in that proof never being submitted to the network, and then we would incur the associated penalties or loss of opportunities by not having the reward from winning post. If we stop the markets node when the client's updating or downloading data, then, well, we may lose business if we lose out on deals. Or we can end up with reputational damage if clients start saying, well, it keeps going offline and we just don't trust that storage provider anymore. It's not a good service. We just got to make sure it stays on. And then questions. That's the end of my presentation. So part 2 will be hosted by Benjamin. And thank you for listening.